welcome to another WJEC A level physics question. This time it's from June 2013's Unit 2 paper, and it was question 7, and it's a question about radiation from stars, which is now on Unit 1 of the WJEC specification. First part of the question, we've got spectral intensity against wavelength graph for one of the hottest stars known, HD 93129A in the Carina Nebula. First part we've got to do is state which part of the electromagnetic spectrum the wavelength of peak emission lies. Well, here the peak is at a wavelength of around about 55 nanometers or so. I mean, we're looking up here. And 55 nanometers is shorter, but not too much shorter than the 400 nanometer violet end of the spectrum. So this must be in the ultraviolets part of the spectrum. Next, we're asked to show that the temperature is approximately 50,000 Kelvin. So here we can use Wien's law, where lambda max is W over T. So T is W over lambda max. W is Wien's constant, 2.9 times 10 to the minus 3. We just said that lambda max was about 55 nanometers, so we mustn't forget the 10 to the minus 9. Otherwise, we're not going to get any kind of sensible answer here. So let's put those numbers into the calculator and see what we come up with. And we end up with 52,700, so roughly 53,000 Kelvin. And all we had to do was show that it was about 50,000, so our answer is roughly right. You might have read the peak as a slightly different value there. WJEC will give you sort of half a square either side there, or maybe if they're generous, a whole square either side. But try to read peaks values off graphs as accurately as possible. Star is blue. We've got to explain how this can be deduced from the spectrum. Well, what we're going to do is, if we imagine following this curve onwards until we hit the visible part of the spectrum. The visible part of the spectrum is 400 to 700 nanometers, roughly speaking. And this curve is always on the way down, so we're certainly going to have a greater intensity at 400 nanometers somewhere over here than 700 nanometers somewhere further to the right. So that will be a possible way of explaining the answer. And we can also explain the answer in terms of the fact that the peak is at lower than the blue end of the spectrum, or it's to the left of the blue end of the spectrum. So let's put it that way. I'm going to put here 400 nanometers just for reference. Okay, the question then continues. B part 1, we're told the distance that the star is away from the Earth is 7.1 times 10 to the 19 meters, and the intensity of the radiation reaching the Earth is 3.3 times 10 to the minus 8 watts per square meter. And we've got to show that its luminosity is approximately 5 times 10 to the 6 times the power of the Sun. And the Sun's luminosity is 3.84 times 10 to the 26. So one point here is to remember that luminosity is another name for power, which is pretty obvious from P Sun and the units of W here. So first of all, as soon as we see this word intensity and this unit of watts per square meter, we know that we're going to have to use the intensity formula, which is not in the data book. The intensity being power over area, or power over 4 pi r squared. If we rearrange that, we've got P is equal to I times 4 pi r squared. So the intensity is 3.33 times 10 to the minus 8. Times 4 pi times 7.1, the distance from us, times 10 to the 19, all squared. So let's substitute that into the calculator and see what we come up with for an answer. So that gives us about 2.1. Let's go for 3 figures because the rest of the data is 3 figures. 2.11 times 10 to the 33 watts. And if we divide that by the power of the Sun, so we can get a ratio, 2.11 times 10 to the 33 divided by 3.84 times 10 to the 26. Just storing that number in a memory first of all, just in case I need it in a minute. Right, so we're going to divide that by 3.84 times 10 to the 26, and we end up with about 5.49 million. So let's say 5.5 times 10 to the 6, which is roughly what we were asked to do in the question, showed that the luminosity was approximately 5 million times the power of the sun. Next part of the question, final part of the question, we're asked to use Stefan's law, which is P equals 4 pi r squared sigma t to the 4, to find the star's diameter. So let's rearrange the equation. So first of all we get the radius. The radius is going to be P divided by 4 pi sigma t to the 4, and all of that is going to be square rooted, and then the diameter is going to be twice that answer. So let's substitute in the values. Always show a substitution. That way the examiner can give you some credit if you manage to mess up the calculation. Value of sigma is 5.67 times 10 to the minus 8 given in the data book, and the temperature we had was about 53,000, and I'm going to use the answer from earlier in the question to get this here. So give me a moment to put all this into the calculator. .11 times 10 to 33. And we end up with 1.96 times 10 to the 10 meters. Finally, the diameter will be double that. So we get 3.91 times 10 to the 10 meters. So, looks complicated question with a complicated formula, but as long as we're careful, we should be able to get the answer out fairly easily. Thank you for listening. Please remember to like and subscribe, and add any comments to the notes underneath the video. Thank you.